To everyone. So today, for today's lesson, we are going to learn about halogenoalkanes. This is going to be after we have done our organic chemistry, and then hydrocarbon. So I'm going to do a revision on halogenoalkanes. So let's start. When you look into halogenoalkanes, the general formula that you can get for halogenoalkanes is CnH2n plus 1x, where X can be your group 17 elements, chlorine, bromine, and iodine. So you, let's say, for example, if I have 2 carbons, and then I have Cl. So how do I use the formula? Basically, it's supposed to be Cn, N is going to be 2 carbon. So C2, H2 times 2, 4 plus 1. So it's going to be 5. X is going to be Cl. So you see this one, C2, H5, Cl. So this is how you use that. And then to give names and so on, you need to learn, how to name the halogenoalkanes accordingly. This one we will skip. So this is going to be halogenoalkanes. And what is going to be the reactions that we are going to study for halogenoalkanes? The reaction, the mechanism of the reaction that we are going to study for halogenoalkanes are going to be 2 actually. Nucleophilic substitution reaction and elimination. So we will start with nucleophilic substitution reactions. For nucleophilic substitution reactions, we are having 3 examples, 3 reactions. I've written over there aqueous alkali. Or you can just in your book they use sodium hydroxide. KCN in ethanol, ammonia in ethanol. We will go and look into it in detail. But before that, let's do some questions. So what is the name of the mechanism for the following reactions? So if you have ethane, ethane which is going to be alkane, with bromine gas under the presence of sunlight, you need to know what is going to be the mechanism of this reaction. So maybe I'll ask my own students first. So maybe Michelle Wee, can you tell me what is going to be the mechanism of the reaction? Ethane with bromine gas.
Is it free radical substitution?
Yeah, correct. Okay. Yeah, correct. So that is going to be free radical substitution. So we have learned about this as well in our previous lesson. And when you have ethene with bromine gas at room temperature, maybe Josh, Josh, what is going to be the mechanism of the reaction?
Is that electrophilic addition?
Yeah, so it's going to be electrophilic addition. And when it comes to this ethanol, where later we will learn about ethanol, ethanol with SOCl2, ethanol, alcohol, and halogenoalkanes, they share the same mechanism, which we will study today, which is going to be nucleophilic substitution. So you can memorize this, nucleophilic substitution. And then the last part, I think when last time when you learn about carbonyl compounds, propanol with HCN, that is going to be your, this one is going to be nucleophilic addition. Maybe this one is going to be something that you can recall, what we have learned. For those who are taking down notes, don't worry, I will give you this, I will send this PDF, the one that I've written to your teachers. Your teachers can send it to you, or you can find it from the Google site. So I'll just move on. The first reaction, because just now I told you, you have this nucleophilic substitution reaction. And the first reaction that I'm going to discuss over here is using sodium hydroxide, which is going to be heated under reflux. And what is heated under reflux? You need to know what is heated under reflux. And you can see the notes that I've written over here. Reflux is going to be heating an organic compound without evaporating off the volatile compound. Volatile means they can change into gas easily. So when I want this halogenoalkane reacting with sodium hydroxide, for example, I don't want the halogenoalkane just simply evaporate. I want them to stay there and react completely with the sodium hydroxide. So when they change into gas, okay, the water jackets or the condenser over there is going to ensure that, okay, the gas change back into liquid. They condense and drop back over here, and then they continue reacting with the sodium hydroxide. So that is the meaning of reflux. Okay. So when you have this halogenoalkane reacting with sodium hydroxide, do remember aqueous solution. Yeah. What will happen is a substitution reaction. So this OH, they will substitute the Br. So you are going to get OH, Br comes out, and then they will join with Na to give you NaBr. Simple as that. In this case, you can remove the Na. Okay, you can just say it's going to react with the OH minus to give you Br minus. Okay, in this case, when we say nucleophilic substitution, the nucleophile that is involved over here is going to be the OH minus, okay, or the hydroxide ion. And how they behave as a nucleophile, you need to know the definition of nucleophile at the first place. Okay, nucleophile is defined as a species that has lone pair. Okay, that has a lone pair of electron. Okay, they can donate the pair of electrons to others. Okay, so always remember this. And some students, they just remember, oh, nucleophile must be negative ion, not necessarily negative. Okay, please remember this. As long that they have lone pair of electron, they can behave as nucleophile. Okay, they can behave as a nucleophile. So I'll just move on here. Okay, that is going to be the nucleophilic substitution reaction with the sodium hydroxide. But there is another type of reaction similar to that. Okay, but I'm not going to use sodium hydroxide. I am going to use silver nitrate. Okay, solution. Okay, silver nitrate solution, similar situation, heated under reflux. Okay, but okay, there will be a different kind of reaction that is going to happen, slightly different, not totally different, slightly different. We call it hydrolysis. What is hydrolysis? Breakdown using water. Again, okay, reflux, you can see we are going to use this setup of apparatus. Okay, but the only difference over here was, okay, you can see that the OH is the nucleophile in the beginning. But now, okay, it is not going to react with Ag plus. It's not going to react with NO3 minus now. It will react, okay, with the water in the aqueous, okay, in the solution itself, where water is going to become the nucleophile now. Why water is a nucleophile? You should know. Okay, water has two lone pair. That's the reason why water is nucleophile. And they are neutral. Okay, they are neutral. And you can see that they are going to react, okay, with the halogenoalkane. Now, let's look at halogenoalkane first, yeah? So CH3, okay, CH2, and then you have Br. What happens over here is, okay, the Br, being electronegative, they are going to withdraw the electron to itself, okay? So that is the definition of electronegativity. Ability, okay, to attract bonding pair of electron in a covalent bond, okay, in a covalent bond. So it means you are attracting the bonding pair of electron. So when they go over there, this is going to be delta negative, partially negative, and the carbon now will become partially positive. So what is nucleophile? Nucleophile is attracted to nucleus. Nucleus is positively charged. Therefore, okay, you can have OH minus, okay, you can have water, okay, because they have the lone pair, okay, they can be attracted over there. But the level of attraction is going to be different, okay, because it's negatively charged. OH minus is negatively charged, and then the delta positive of the carbon is going to be positively charged. Opposite charges attract. Okay, it means this bond can be formed better, okay, compared to the bond between water. That is the reason why, okay, the reaction between the nucleophile with OH minus is faster. It means this reaction is fast compared to this reaction, which is going to be slightly slow. You see, hydrolysis is slower than sodium hydroxide. What is the reason? Because the negatively charged hydroxide ion is more effective as nucleophile compared to neutral water molecules. Okay, so this one you need to understand. Okay, you need to understand, but okay, please remember one more thing. Okay, when this reaction is happening, the Br, okay, is still going to be a substitution reaction. The OH is going to go and take place, okay, over here, and then the Br will come out, okay, and then the H and the Br will join together to give you HBr. Okay, you can see they have written in ionic form over there. Now, the reaction do not stop over there. Okay, what will happen is the HBr, now they will join with the silver nitrate, because just now you added silver nitrate. So the silver nitrate, okay, the silver bromide is going to be formed and HNO3 will be formed. And I have discussed this in the first lecture or second lecture before this. Okay, you need to know, okay, as a AS chemistry student, okay, or chemistry student for A level, you should know AgCl, AgBr, and AgI. They are actually will form precipitate, and you should know what is the color of those precipitate. The color of AgCl is going to be white. The color of AgBr is going to be cream. The color of AgI is going to be yellow. Okay, I keep on repeating the same thing because very, very important. Okay, so this is going to be the observation. So let's look into this checkpoint. Let's see what we have learned so far now. Okay, compare the reaction, okay, between bromoethane with sodium hydroxide solution, and I want to compare with bromoethane with silver nitrate solution. Okay, so how do I compare both reactions? So I just put over here. Okay, I have sodium hydroxide aqueous, and I have the silver nitrate, okay, which is also aqueous. So when I compare, you need to compare, let's say, what is the similarity? Okay, what is going to be something that is different? Okay, so similarity, I can see that both of them require heated under reflux, okay, because you're dealing with volatile compound. Okay, but what else do I notice? Okay, I will notice that both of these reactions, okay, they are going to produce alcohol. Okay, they are producing alcohol. You can see, okay, they are producing alcohol. Okay, they are producing alcohol. So that is going to be some sort of comparison. Okay, but when it comes to nucleophile, okay, I'll just put N over here. When it comes to nucleophile, there's going to be difference. Okay, the nucleophile is OH minus. The nucleophile over here is water. If you compare whether they are going to be fast or slow, okay, because this is negative, this is going to be fast, and this is going to be slow. What will happen? What do I see? Okay, when I have this reaction, I won't be able to see anything because all of them are colorless. Okay, no precipitate. So I can say that, okay, there is no precipitate. But, okay, for silver nitrate, after they react, okay, I'm going to get HBr. Both of them are going to be colorless, okay, but the HBr, they don't stop. They will react with silver nitrate. So there will be possibilities of having this, let's say, for example, AgBr, AgCl, AgI, and so on. So there will be a possibilities of having precipitate, depending on what you are using, okay, depending on what you are using. So in this case, I'm using bromoethane and silver nitrate. So I'm talking about precipitate, which is going to be silver bromide, which is going to be a cream precipitate will be formed. So you can differentiate them. Okay, very, very important. Okay, very, very important that you know. Okay, but generally we categorize them as one reaction. So we don't, because they are almost similar. Okay, almost similar. Okay, so we categorize them as reaction 1 for nucleophilic substitution. Okay, so let's move on. Okay, for the second part, nucleophilic substitution. Okay, but now I'm going to use KCN. Okay, similar, heated under reflux. Okay, but addition is going to be ethanol. Just now, I don't use ethanol. Okay, but this one, okay, I need to use ethanol, heated under reflux. Okay, and if you don't know what is reflux, I still put it over there. Yeah. So what happens? Okay, generally the CN is going to be the nucleophile. Okay, they will just substitute this like normal. Okay, they substitute. Okay, but what is additional stuff over here is in the beginning, you have 2 carbon only, okay? So now, when you react with KCN, okay, in ethanol under reflux, you are adding the number of carbon in the compound. Okay, it means now you have 3 carbon. Okay, so this one, when you want to name, okay, it's going to be 3 carbon propane. So you just add nitrile. Nitrile, whenever there is CN group, you just put nitrile. Okay, so propane nitrile. Okay, so this is going to be very important because they say that, okay, when you have KCN, okay, you are adding the number of carbon. Now, do not get confused, okay, or if you recall, oh, I think I learned something like this also, yeah. Maybe you are talking about, okay, carbonyl compound. Now, carbonyl compound, okay, they do react something similar, but not exactly KCN. Okay, you need to remember. Okay, they will react, okay, with HCN, carbonyl compound. Yeah, so I'll just put carbonyl compound. So maybe it can be aldehyde, it can be ketone, because only one reaction only we learn for carbonyl compound. Okay, under nucleophilic addition. Okay, but this HCN is prepared, okay, from in situ. Later we will learn. In situ means in the same reaction vessel, okay, by using NaCN, okay, with H2SO4. Okay, you can prepare them, okay, using this, and then they will react. Okay, they will react. So I'll leave it for your own reference. Okay, where you want to check, you can check. But this one is going to be different. KCN in presence of ethanol under reflux. Okay, so this is slightly different than the one that you have learned in carbonyl compound. Yeah, you can go and read more about this. So number 3. So I recall again. Number 1, okay, we have learned reaction with NaOH aqueous, and I also mentioned about AgNO3, which is going to be aqueous. Okay, we talk about OH minus, we talk about water as being the nucleophile. Yeah, so the second reaction is going to be if you are using KCN, ethanol, and then you heat them under reflux. The same. Number 1 also heat under reflux, but not with ethanol. Okay. But now number 3 is going to be by using ammonia. Okay, heat under not reflux pressure. Yeah. Okay, so do remember. If you cannot remember, just think like this: alcohol or halogenoalkane. Most of them you need to heat with under reflux. Okay, but only some. Okay, like maybe this reaction in your textbook they say heat under pressure. Okay, it means you need to use high pressure for this. Okay. So you are going to be another important thing that you need to take note is going to be excess. Ethanol, yes, definitely it's going to be important, but it must be in excess, ammonia. Okay. If you look at the reaction, okay, you can see ammonia, okay, is a nucleophile. Why? Because they contain lone pair of electron. Okay. When they react, okay, substitution, okay, so this one, Br will be replaced or substituted by NH2. So one of the hydrogen, it will react with Br to give you HBr. So you are going to get amine being formed. And the ammonia, okay, just now I mentioned it must be in excess. Okay, why it must be in excess? Very simple, okay, because we know bromoethane, okay, is going to be the carbon over here is delta positive. They are going to accept, okay, any nucleophile coming in. Do remember, one of the product as you are forming is also the ethyl amine. It's also having lone pair of electron. They also can behave as your nucleophile apart from ammonia. So I don't want, okay, the ethyl amine, the product, to compete with ammonia to attack bromoethane. I don't want that. I want only ammonia to go there. How do you do that? You eliminate competition by making this a lot. Okay, you put a lot of ammonia. Okay, and that is going to make sure that the ammonia is going to be the nucleophile that will react with the bromoethane. Okay, so excess of ammonia is going to help out where you can eliminate the probability of having a mixture of products. Okay, so we don't want the product to behave as a nucleophile. Okay, so that is going to be the explanation for this. Okay, so let's look at the mechanism. Okay, so now, okay, I have taught you 3 things: the reaction with NaOH, okay, AgNO3. I have taught you about KCN, and I have taught you about ammonia. excess ammonia in ethanol. Okay, now let's look into the mechanism of nucleophilic substitution. How does it work? Okay, how does it work? Now, in order to identify that, or in order to learn more about that, you need to look into the structure of halogenoalkane. Okay, if you have carbon attached to the halogen, okay, that carbon can be attached to all three hydrogen, or sometimes you can have one R group. What is R group? CH3, C2H5, okay, one R group. If you have one R group, that is going to be known as a primary halogenoalkane. If you have two R group, then it's going to be secondary halogenoalkane. If you have another R group, okay, then it's going to be tertiary halogenoalkane. So R here cannot be hydrogen. Okay, cannot be hydrogen. So here, okay, you need to understand about that concept. Okay, and we have only two types of nucleophilic substitution. SN means nucleophilic substitution. Only two types, SN1 and SN2. Okay, you need to remember. Okay, SN1 is for tertiary halogenoalkane. I want you to remember this. Okay, it's like, okay, you have primary, secondary, tertiary. SN1 straight away will go to the tertiary. Okay, you can memorize this. And SN2, okay, is going to be straight away, okay, will be for primary. Okay, will be for primary halogenoalkane. Okay, some of you will ask, how about secondary halogenoalkane? Secondary halogenoalkane can undergo SN1, SN2, no problem. Okay, you can choose whichever it wants to follow. But tertiary halogenoalkane must follow SN1. Primary halogenoalkane must follow SN2. Okay. Now, to follow through this, okay, you need to also learn about one more stuff, which is going to be something related to your carbocation. I'll explain about carbocation a little bit. Yeah. Now, if you have one carbon, okay, and I have one hydrogen, and one R group. Okay, this is called primary carbocation. Okay, primary carbocation. And if I have, okay, two R groups, okay, if I have two R groups, this is going to be a secondary carbocation. If I have three R groups, that is going to be my tertiary carbocation. Now, always remember, okay, tertiary carbocation is more stable compared to secondary, compared to primary. Okay, and I always like to actually represent this in a simple way. How? Okay, imagine, okay, you have one person who is being very, very sad. Okay, who is being very, very sad. And you are sharing your feeling to only one person. Okay, you are sharing your feeling to only one person. Okay, and you share your sadness to him. Okay, the same, okay, if you are sad, okay, and you are sharing your feeling to two persons. Okay, you share. Okay, maybe these people also will actually comfort you. Okay, comfort you, and you are not going to be that sad. Yeah. But if you have three people, way better. Okay, three people telling you life is good. Okay, no need to worry. Okay, and you'll end up being happy. Okay, you end up being happy. Why? Because you're sharing your sadness across three people, which is better. Now, do remember, our group is something that can donate electron. They will give you electron. Okay, they will give you electron. And in chemistry, okay, whenever something giving electron, okay, we call it as positive inductive effect. Okay, positive inductive effect. So this has, okay, like for example, this tertiary situation, it has a better positive inductive effect, okay, making this carbocation to be more stable. Why? Okay, because the positive charge is going to be shared across three different groups. Rather than just being concentrated at one particular place. Okay, if that is happening, okay, it means that this particular carbocation is going to be very, very stable. Okay, that is the reason, okay, if you have 3 people, you are sharing the sadness to 3 people, you will become very happy. Okay, so you are going to be more stable. Okay, so that is the explanation over here. So always remember, tertiary carbocation, okay, is something that always they want to form tertiary carbocation compared to secondary, compared to primary. Now, coming back to this situation, we know, okay, that halogenoalkane will donate, yeah, the electron. Okay, it means the electron will be withdrawn to the halogen, okay, making this delta negative and delta positive. It means that there is a possibility that carbocation can be formed, okay, for primary, secondary, and tertiary. If you have 3 R groups, okay, which is tertiary halogenoalkane, they will have tendency to form carbocation. Okay, so coming back here, if I have tertiary halogenoalkane, no need to think anything. Tertiary halogenoalkane, they will form carbocation. Primary, can they form carbocation? No. Okay, so they will form something what we call as intermediate. So this one you need to remember. Okay, Sn1 is for tertiary, tertiary will form carbocation. Sn2 is for primary, they will form intermediate. Yeah, so let's actually move on. Yeah, so Sn1, let's look at the formation of this carbocation. How will they be formed? Okay, so you can see, okay, ignore the 2-step reaction. Later I'll explain about that. Okay, what is going to happen in the beginning? Okay, this one, okay, will withdraw the electron. So delta positive, delta negative, and delta positive. Okay, and you can see that they have, okay, they have 3 R groups. It means tertiary halogenoalkane. They will form carbocation first. Carbocation is being formed. Okay, so this is tertiary. So of course they are going to be Sn1. You can see Sn1. And then, okay, this Br, okay, is already out, okay, and you have another nucleophile, which is ready to react, okay. So let's say we look at NaOH, so the OH nucleophile, they go and react, and then you are going to get the alcohol and this, okay. So you can see that it is slow and it is fast, okay. That is going to be 2-step reaction, okay, because from this product, you form a product, and then you form another product. So it's a 2-step reaction, okay, 2-step reaction. But, okay, if I have Sn2, what will happen? This is going to be very interesting also, okay. The Sn2, you are going to do formation of intermediate, okay. What will happen? Okay, you can see here, okay, this is the Br and C, so this is going to be primary, okay. The carbon is attached to 1 R group, so it's going to be primary halogenoalkane. So you are going to follow Sn2 mechanism, okay. Sn2 mechanism is formation of intermediate. So what happened? The delta positive is there, the OH minus will come, okay, and then the formation of the bond is not complete. The breaking of the bond is not complete. That is going to be, they put it as a dotted line, okay? And then after that, okay, you will form bonds, okay, for OH, and you will break the bond between Br, and you are going to get this, okay? Now, this is going to be known as not a here you see 2-step. This is actually 1 step. Now, some people, some students will say, it's so difficult, 2-step reaction, 1-step reaction, but there's still 2 arrow. How? Yeah, this one, okay, in order to understand better, okay, just take it like this, okay. You have husband and wife, okay. They are not happy with each other, okay. They are not happy with each other. They decided to go separate ways, okay. Go separate ways. So you become available. So another lady come in, okay, in the life, get married and join together, okay. It's 2-step, okay. You get rid of the person and you marry another person. It's a 2-step reaction, okay. But for this one, it's like very different. This person is not happy with the wife and decided to play around, okay, another person come into the life, okay, and started to build the relationship, and he is not fully separated with the wife, okay, and you can see that that is going to be the intermediate, and this is not a particular state that is fixed, okay, it's not constant, so you can assume that it's just one process only along the way, yeah, along the way. And this is going to actually result in, okay, this one will be broken and then joined together to give you this. This is going to be Sn2, okay, Sn2 mechanism. And this one, okay, even last time when I teach my students, okay, there is a question, okay, when you have energy level, okay, when they actually draw the energy level like this, and then they say there are two types of activation energy. Okay, there are two types of activation energy. Whenever there is a two types of activation energy, okay, or you have like something like this, only one. Whenever there is two types of activation energy, like there is a loop over there, okay, this one belongs to, okay, Sn, okay, Sn1. Okay, why? Because there is a state, something there, okay, and this is going to be a two-step, step number one, step number two. This one single step, okay. So this one belongs to Sn2. You can see in the passe paper, yeah, there is going to be a question on this, okay. But now, okay, going back to this, our checkpoint. Now, draw the mechanism of the reaction between 3-chloro-3-methyl pentane. In order to do this, pentane, okay, 5, and then 3-chloro, okay, Cl, and 3-methyl. And I want to draw the mechanism. So first of all, identify Sn1 or Sn2. Okay, you can see that it is going to be 3 R groups. Okay, the carbon has 3 R groups. So it's going to be tertiary. So Sn1, carbocation will be formed. So what you do, you form the carbocation first. CC, this one plus KCC, CH3. Okay, you form the carbocation first. After that, okay, you are going to be initially, I think I missed this one, delta positive, delta negative. Okay. And then you put the OH minus, okay, and then put over here. They will come and then they will join, okay. I'm very sure you can draw yourself, okay. So OH and then CH3, you will have something like this. And this is going to be, you can see it's going to be a two-step reaction. So this one is going to be slow. This is going to be fast. Okay, you can memorize quite easily. Yeah. So number 4, okay, draw the mechanism of the reaction between 1-chlorobutane, butane. So 4, okay, 1-chloro, so 1. Okay, this is hydrogen and hydrogen. You can see 1R group. Okay, so primary halogenoalkane. Primary halogenoalkane will form intermediate. Okay, so what if I have KCN? So it means they will have CN minus, okay. So I will have this one delta negative, delta positive, okay. So they will go and join first, okay. So what will happen, okay, you are going to have C, this one maybe C3H7, I just simplify, okay, I just put H, okay, that is going to be Cl, that's going to be Cn. So this is going to be intermediate. And next is going to be, it will form the product itself, C3H7, CH2, and then the Cn will come in, and then you'll have Cl dot dot. Okay, so that is going to be the mechanism. Okay, you need to know how to draw the mechanism. So I'm done. Okay, you see here. Okay, for nucleophilic substitution, there are 3 reactions. Okay, you can see sodium hydroxide and silver nitrate. Okay, KCN, ethanolic reflux. Yeah, excess ammonia, ethanolic under pressure. These are all nucleophilic substitution. Okay, but when I started just now, halogenoalkane, I mentioned that they also have another type of reaction, which is going to be known as elimination reaction. Okay, for elimination reaction, okay, the reactant that we will use is almost the same, sodium hydroxide, but the difference is you put ethanol. Okay, just now I don't put ethanol; it must be aqueous. Okay, but now I use ethanol and then I use reflux, heater under reflux like just now. Okay, but whenever you have that, okay, you are going to have elimination. So how elimination works? Okay, you have CHBr and then CH3. So I put like this. Okay, what happens is the H and the Br will go out. Okay, and they are going to give you the double bond. Okay. And this HBr, they will join, okay, Br will join with Na to give you NaBr. H will join with OH where they are going to give you water. Okay, so the difference over here is, okay, rather than forming alcohol, you are eliminating the presence of alcohol, okay, the ethanol is going to cause elimination reaction. Okay, so you are not going to have nucleophilic substitution, you are going to have elimination reaction. Do not confuse with elimination and just say elimination is part of nucleophilic substitution. That is wrong. Okay, this is going to be different. You are removing, yeah, so it's going to be elimination. Yeah, so checkpoint 5. Okay, let's see. Okay, if let's say I'm going to write equation for the reaction of 1-chlorobutane, okay, with sodium hydroxide aqueous under reflux, sodium hydroxide ethanol under reflux, so they are going to be different. Yeah, so chlorobutane, so maybe butane, okay, so 1-chloro, so I just put like this. Okay, maybe I will use CH3, I'll write down in structure form, CH2, CH2, CH2Cl, okay, plus OH minus the NaOH. It is going to be a substitution reaction. So CH3, CH2, 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 OH plus Cl minus. Okay, that should be the equation. Now, but when it comes to this elimination, I will suggest you put the Cl over here so that it's easier to be seen. Okay, hydrogen, hydrogen. Maybe I just put another hydrogen over here. What will happen? Okay, the hydrogen and the Cl will go out. Okay, and you will get a double bond. So maybe I will write down, okay, the same thing earlier, CH3, CH2, CH2, CH2Cl plus, okay, when you add with, let's say in this case, I need to put NaOH. Okay, I'll just put. Okay, and then what am I going to get? I will get CH3, CH2, and then CH. There is going to be a double bond there. You can show the double bond. Okay, and then I have CH2 plus, okay, this H will join with OH to give you water. That Cl will join with Na to give you NaCl. So this one, if they ask you to write equations, okay, please take note. Checkpoint 5. Okay, let's try past year questions. Yeah? Now, which organic reaction is an example of nucleophilic substitution? Example. The first thing, nucleophilic substitution is for alcohol and halogenoalkane. Not alcohol, not halogenoalkane, eliminate. Halogenoalkane, okay, fine. Sodium hydroxide, okay, fine. Okay, you have alcohol to give you alcohol, NaBr, okay? We have learned about this. Okay, we have also learned about this. Okay, but what can you say about A? This is going to be elimination because you are forming the double bond. Okay, you are removing the HBr and getting this elimination, which is going to happen with the presence of ethanol. Okay, this is the one which is going to be in aqueous form. Okay, so if they ask which one is an example of nucleophilic substitution, the answer is going to be B. Very simple. Okay, next, which statement is correct about Sn2 mechanism? Now, Sn2, okay, I told you Sn1 is for tertiary, Sn2 is for primary, tertiary will form carbocation, primary will form intermediate. This information is good enough to answer this question. Okay, so one bond is broken at the same time another bond is being formed, correct? Intermediate, remember? Okay, you haven't fully separated from the wife and started to actually having an affair. Yeah, so it's going to be one bond is broken at the same time the another bond is being formed. So correct. Okay, number 1 is correct. The formation of intermediate involves collision of two molecules of ions. Yes. Okay, they are going to collide. Okay, the ion that they are talking about is going to be the nucleophile, and another one is going to be the molecule. Yeah, they collide. So this is correct. A carbon atom in the transition state is bonded either fully or partially to 5 atoms. Correct. Okay, you can see that they have 5 atoms over here. Okay, 1, 2, 3, 4, 5. Okay, there are total 5 atoms bonded to that carbon. Okay, therefore that is also correct. Okay, so you will have the answer is 1, 2, and 3. Okay, let's move on. Now, bromoethane is heated under reflux with concentrated aqueous. I think the most important thing is aqueous sodium hydroxide. Now, aqueous sodium hydroxide, you are going to get nucleophilic substitution where you are going to get alcohol. Okay, but let's say they say bromoethane. So bromoethane, so this is Br. Okay, so when I have this bromoethane, what will happen? When you react, so you will get OH. In this case, okay, what will happen? I need to check, okay, this is going to be a primary alcohol. Okay, so a major product is primary alcohol, correct? And we know this is going to be a primary halogenoalkane. Primary halogenoalkane will always undergo Sn2 mechanism, correct? The major product will be the same if NaOH is dissolved in ethanol. You are not going to get alcohol. You are going to get ethene. Yeah, you're going to get ethene. So we don't want to that to happen. Yeah, so that is not going to happen also. Yeah, the answer is going to be 1 and 2. Okay, next. Some reactions based on 1-bromobutane are shown. So this one is going to be some mixture of questions. Okay, but I selected some of it that we have learned so that we can also see over here. Okay, so they say that the first thing is complete the diagram to show the Sn2 mechanism. Okay, for reaction 1. So Sn2, okay, Sn2 is supposed to be for primary halogenoalkane. Let's see whether this is primary or not. Okay, CH3. Okay, then you have CH2, 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 then Br. And you can see this is a primary. Okay, so primary halogenoalkane reacting suddenly, this part is changed with OH. So if it is changed directly with OH, we are talking about substitution. Yeah, and what kind of substitution? So we have learned NaOH. Okay, if you want to have nucleophilic substitution, it must be in aqueous, heated under reflux. Okay, we have already learned about this. Okay, no need to use alcohol over here. Okay, but now I want to show, okay, this reaction primary here. Primary cannot form carbocation. We are talking about intermediate. So how do you show this? Okay, first of all, okay, this one, delta negative, delta positive. And you need to show intermediate. So I just put OH minus. This one, okay, will go over there. Okay. And what will happen next? Okay, it's supposed to be dotted lines. Okay, will supposed to form. Okay, so maybe I'll just put like this. Hold on. This one, okay, maybe they put OH over here. Maybe I'll just put, there will be a dotted line, okay, with the Br. Supposed to be a dotted line over here also. Yeah. The next step, okay, supposed to be completely changed to what is given over there. Okay, which is going to be plus, okay, Br minus. So maybe I can just simply add another one more here, H, and then I put dotted line Br, dotted line OH. This is the intermediate. Okay, so this will be representing the diagram and you will be able to get the 2 marks over there very easily. Yeah, next. 2-bromo, 2-methylpropane. Methylpropane. Okay, so CH3, 2-bromo. Okay, you can see that, okay, they have 3 R groups. So it's tertiary now. Okay, so if you have tertiary halogenoalkane, okay, just now SN1, okay, now tertiary, okay, sorry, just now it's SN2, okay, tertiary will always follow SN1 mechanism. And the moment you see or hear about tertiary halogenoalkane, you must talk about tertiary carbocation. So it means they will form carbocation. So what is going to be, okay, later we'll explain about that. But here, I think I'll skip this part because this is revision on the first part, which is we have learned about organic chemistry. Yeah? Define the term structural isomer. Structural isomer is going to be a isomer that has the same molecular formula but different structure. Types of structural isomer. Yeah, we have position. Okay, we have functional. Okay, we have chain. Okay, I have went through this last time. Yeah, with you. Okay, but now, okay, coming back to this, maybe I'll just select this. Okay, and then I will bring it down. Okay, so here. Now, so here, okay, the same thing. Okay, they are going to react, and suddenly you are going to get methyl propan to all. Identify the mechanism for this reaction. Now, the mechanism for this reaction is going to be, you are going to have SN what? Okay, so this one must be SN1. SN1 nucleophilic. Okay, SN1 nucleophilic substitution. And explain why this reaction proceeds with different mechanism, because just now was SN1. SN2. Okay, why now is SN1? Okay, the answer is because now, okay, you have a tertiary a tertiary halogenoalkane, and a tertiary halogenoalkane will have tendency to form a stable carbocation. Okay, and therefore, okay, they will undergo SN1 nucleophilic substitution. Okay, so you just mentioned about that. So it means with two key points. Okay, the two key points are going to be, you talk about this is going to be a tertiary halogenoalkane, so one. And the second part, you need to talk about it will form carbocation rather than intermediate. Okay, so 2 points. Okay, you will get it over there. Next. Now, some reactions are shown, okay, over here. Okay. And for each of these reactions, state the region and so on. You can see here, this is alcohol. Okay, and then suddenly I have halogenoalkane. Okay, but it can go the other way around, which is something that we have learned today, reaction 2. Okay, you have halogenoalkane, okay, changing into alcohol. Okay, and alcohol also changing into this. So this is going to be reaction of alcohol. Okay, and this one is what we have learned last time, which is going to be alkene, okay, will react with HBr, okay, and then they will have this and this. So you have different products, okay. So one will be major, one will be minor, okay, electrophilic addition, okay. So here, okay, I have the marking key over there. You can go through, okay, but you can see I'm interested for now, okay, related to today's lesson, reaction 2. Okay, what is reaction 2? Reaction 2, when you have halogenoalkane changing into alcohol. Okay, so that is going to be, you are going to use aqueous, okay, potassium hydroxide if you want, okay, but in your syllabus, in your textbook, okay, NaOH, okay, you put over there. And type of the reaction, okay, you look over here, what type of reaction? Okay, this one is going to be nucleophilic substitution. You can use this, okay, nucleophilic substitution. They do accept hydrolysis, okay, but I will suggest to use substitution, yeah, substitution. Okay, the rest, okay, you can go through, okay, when we learn about alcohol, okay, when we learn about, okay, even I think reaction 4, I can go through with you, okay, you can see that the region is HBr, okay, and when HBr, the type of this reaction is electrophilic addition. And then the condition, I think you should know, is room temperature. Yeah. So please go and read about, okay, the alcohol part. Yeah. We will, we supposed to have a lecture on that. Okay. But I think your teacher will cover, okay, related to alcohol, okay, during the lesson next week or tomorrow, starting from tomorrow. Yeah. Draw the diagram to show SN1 mechanism for reaction 2. Okay. Reaction 2. I want to show SN1. Okay. So you see CH3. And then Br, you can see that they are tertiary. Tertiary must be SN1. So it means they are talking about carbocation. Okay. So what you need to do, you just put this one delta negative. This is going to be delta positive. So you are going to write down this first. This is going to become the carbocation first. Once you get the carbocation, okay, so you have the Br minus here. And then you are going to react, okay, with the OH. So I have OH here. And this thing will come and join now. Okay. So I am going to get, okay, CH3, 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 and OH. Okay. So if you want, okay, you can always write down, this is a two-step reaction, which is going to be, this is going to be very slow. This is going to be fast. Okay, because why? This is forming a product. Okay, so even if you want to draw the energy level diagram, it will look like this. Okay, I want you to remember this. Yeah, very important. Now, give two reasons. Okay, in the product in reaction 3. Okay, do not show stereoisomer. So whenever you talk about stereoisomer, you need to consider two things. Okay, whether they are cis or trans, or whether they are optical. Okay, for this, I can see that the carbon attached to the double bond is attached to 2H group. So the moment that they are attached to 2H group, they must be the different groups being attached to that carbon. Okay, so they cannot form cis and trans. So one of the reason, okay, the carbon attached to double bond, okay, is with two same groups, so cannot form. Okay, you can explain more. Cannot form cis and trans. Okay, number two. Okay, you need to talk about the possibilities of having optical isomers. So you need to look for your chiral center. No chiral center, no chiral center, no chiral center. Okay, this carbon, all three are the same. Okay, then only one different. So it means now, okay, the number two is going to be there is no chiral center. So you say there is no chiral center. Okay, you just can explain about that. Okay, next. This one, I think addition to what we have learned. Okay, so I just put over here so that you can also revise. Okay, you see methyl propane can be polymerized to become polyalkene. Okay, so the type of polymerization, you see propene, double bond. Automatically, this is going to be addition polymerization. Okay, addition polymerization, and repeat the unit of the polymer formed. Okay, draw the repeat unit. Okay, so only one, no need to repeat it many times. Okay, draw the repeat unit. Okay, so methyl propene. Okay, so propene. Okay, and then there is methyl, so CH3. So whenever there is going to be something like this, I will advise CH3 put here. This is also CH3, I put here. Double bond. Okay, so C, this is going to be H. So I just put H over here. Double bond will be broken, and then you will get this. So you just need to select this and put it there. That is going to be the answer. And then state the difficulty associated with the disposal of polyalkenes. Okay, they have saturated bond over there. Okay, when you want to dispose, okay, they are non-biodegradable. Okay, why? Because it is not susceptible to chemical attack. Okay, because there is no double bond. Okay, so they are unreactive. Okay, non-biodegradable. Okay, or non-reactive. Okay, so they cannot be broken down. Or if you want to burn them, okay, they release toxic gases. Okay, you can just mention whatever that you want over there. But I think the main answer should be non-biodegradable. Yeah. Now, name the two products of reaction 4 is an extension to that question also, the naming part. Okay, let's actually name them. It's quite easy also to name. Okay, so you have CBr, and then you have CH3, CH3, and CH3. When you name any compound, always name with the longest carbon chain. Okay, so I can see that the longest carbon chain that it can form is going to be 3 carbon. So automatically, this is propane. So if it is propane, carbon number 1, carbon number 2, carbon number 3. So carbon number 2, there is bromo. And there is also carbon number 2 is going to be methyl. So I will draw and I write 2 bromo, 2 methyl. After methyl, no need to put dash. Straight away, write propane. And then the last one, okay, you have CH3, okay, bonded to this carbon, another CH3, and then hydrogen. And I have H and Br. The same, okay, let's actually find out the longest carbon chain. If you find out the longest carbon chain, this is going to be the longest carbon chain, 3 also, yeah. So it's going to be still propane, okay. But, okay, this is going to be maybe position 1, position 2. So which one do we choose, okay? So maybe this one is good. Is it 1 bromo, 2 methyl? Okay, or is it going to be 1 and 2? Okay, I think that's the best way. Okay, so this one is going to be 3. Okay, if you follow here 1, 2, 3. So we don't want to name it 2 and 3. So the best way is to name them as 1 bromo, 2 methyl propane. So 1 bromo 2 methyl propane. Okay. Now, last thing, okay, before we end, okay, I want you to, this is the end, okay, so I just want you guys to complete this, our quizzes, okay, so I will start now, okay, I will put the quizzes in your chat, hold on. Okay, complete the quizzes. And while you're doing this, okay, I will also share to you, okay, the link for my reflection. Okay, I think this one we really want you guys to write the reflection. Okay, because I do notice only a few campus writing the reflection. Okay, please write the reflection. It is very important. Yeah. So the other campus, okay, make sure take the time. If you need time, you just copy this link or open this link in your new tab. Okay, later you can complete it, no problem. Okay, so there are 2 links over there, so I will actually just wait for everyone. Okay, let me share screen here. Okay, I have started. Okay, those who still need to join, okay, please join. Doing, okay, continue to do, okay, during this time, okay, when you join to the other lesson, you can still continue to do, okay, so make sure you save the link, okay, that I shared to you, okay, the reflection is very important, okay, so make sure you put the reflection there, okay, Padlet reflection, okay, please make sure you have that reflection done, okay, thank you guys, okay, that's it for today, okay, see you, bye.
Thank you, Mr. Gopi.
Thank you, Miss.
Thank you, Mr. Gopi.
Good night.